Hello and welcome back to Keen on Maths. So we've been looking through this paper, this 2017 summer paper, and currently we've bashed through a good few pages. So we've done the first 3 pages. So we're now on to question 9. In this video, we're going to do 3 pages in one. So we're going to do from question 9 all the way up to the end of question 13. So as always, I do recommend you actually have a go at this first before you watch me go through it. If you want the link, it's in the description to download this paper yourself and have a try. So let's get started. Now this question is, I always talk about these kind of questions that have so much information, and by the time I get to the bottom, my brain has frozen up because there's just too much information for me to deal with comfortably. So what I want to do is try and break it down. And as I go, once you get used to these questions, once you've seen similar questions like 5 or 6 times, you know like kind of what they want you to do. And before I even read the final question, like right at the bottom, I'm already working out kind of what it wants me to do. So let's take it one step at a time. Sean works for a company. His normal rate of pay is £12 per hour. Now that's clearly going to be quite an important bit of information. I might underline that in the exam, or if you've got a highlighter, highlight it. When Sean works more than 8, so it's got to be more than 8 hours, he is paid overtime. Now the way overtime works is that if you work for longer than the hours you've been given, if they need you to do some extra work, they usually pay you a little bit more to kind of keep going for that longer time. For each hour he works more than 8 hours, he gets this overtime. His rate of overtime pay per hour is 1.25 times his normal rate of pay per hour. Now, I'm already thinking what I've got to do. I've already got a bit of an idea of some working out I'm going to have to do for this question. Without reading this extra line of information, without even reading what the question wants me to do, I've already got some ideas of stuff I can work out, even if I'm not going to use it. Obviously, time is precious, but at the same time, if we're not sure what to do and we're overwhelmed by information, what students usually default back to is, I'm just going to do something with the numbers. I might times them, I might add them, I might divide them. But what we need to do is try to break this down slowly. So have a think so far. We've got £12 per hour as the normal rate. And then for overtime, it's 1.25 times this. So to work out the overtime pay, and this is something else I'd recommend that you do, just write, it just has to be little labels just to help you understand what your steps you're doing and also the examiner to understand what you're doing. So the overtime pay is 1.25 times the normal rate of pay, which is 12. 1.25 times 12. Oh, there's so many ways of doing this. I could talk probably too long about the different methods of multiplying by a mixed number. We could change it to an improper fraction. We could change it to a decimal. We could increase it by 25%, that kind of thing. So let's, for the sake of argument, let's just make it an improper fraction. So in this 1 whole, I've got 4 quarters. Then I've got 1 extra quarter here. So altogether, I've got 5 quarters. And the reason for that is this is my 1 whole. That's going to be worth my 1. If I split that into quarters, you can see I've got 4 of them. And then I actually have an extra 1/4 here, which is this little bit next to it. So if I highlight what I've got all 4 of them in my 1 whole, then 1 extra. So I've got 5 quarters in total. Times by 12, well, 12 as an integer is the same as 12 divided by 1, or 12 ones. So that's a really nice quick way to change an integer into a fraction. And then we are just multiplying fractions. So multiply the numerators, 5 times 12 is 60. Multiply the denominators, 4 times 1 is 4. And I've got 60 over 4. Let's simplify that to 30 over 2. That's me halving the top and halving the bottom, which is 15 over 1. That's again halving the top, halving the bottom. That's what I'm doing there. I need to do it to both, keep it the same. 15 over 1 is 15 divided by 1, or 15 ones. That is just 15 as an integer. So we've got 15 there. Now there's many other different ways to get that bit. I've just shown you one. I thought I might show you some fractions, since I think fraction skills are really good to work on at this stage of your education. So let me, I'll get all this working out that we don't necessarily need now. I might just delete it, you know, just to get some space here. I don't want to run out of space. Because often the working out I do in the videos is like more working out than I would actually do in an exam. Just because I'm trying to show you what's going on. Right, so that is my overtime pay. So that's how much I get paid for overtime. Or Sean does. So let's have a look at this next bit of information. See, I've worked out something already. It's £15 per hour when they're doing overtime. On Monday, Sean worked for 10 hours. Okay, I'm already seeing where it's going. So for 8 of those hours, we're getting paid normal rate. So for 8 hours, it's the normal pay, it's £12 per hour. However, for those extra hours above the 8 hours, I'm getting paid £15 per hour. So I'm getting paid £12 for 8 hours. So I'm going to times that. So I've got £12 8 times. And then after I've done that, I've also got an extra 2 hours. So that is £15 for my overtime pay. And that is an extra 2 hours, because up to 8 hours, and then I've got 2 extra hours to get to 10 hours. And that's going to be my overtime pay of 15. So we've got 12 times 8, that's going to be £96, plus 15 times 2, that's £30. So altogether, it looks like Sean is going to get £126. And I've not even looked at what the question wanted, but I suspect it might be this. Let's have a look. Work out the total amount of money Sean earned on Monday. So that is what we're after. So it's £126. And you see how much it helps to break down the question, to really see each bit of information, see what you can do with it. And it helps you stop getting overwhelmed, because a lot of people look at a question with lots of information and get easily overwhelmed. So that's going to be £126 for Sean. Lovely, let's move on to question 10. A farmer has 20 boxes of eggs and there's 6 eggs in each box. Write as a ratio, so ratio is with 2 dots, the number of eggs in 2 boxes to the total number of eggs. So I'm just going to copy out some information from the question. So number of eggs in 2 boxes, 2, and in maths this little word 2, if you're talking about a ratio, it's going to be those 2 dots, so that means 2. Number of eggs in 2 boxes to the total number of eggs, so I'll just put total eggs. That's what we're trying to work out, and then we want it in the simplest form as well. But worth remembering that it's a 2-mark question. We'll get 1 mark for simplifying it. So how many eggs are in 2 boxes? Well, I've got 6 eggs in each box. So in 2 boxes, that's going to be 2 lots of 6, which is 12. Okay. And then the total amount of eggs. Well, the farmer's got 20 boxes. So in total, we've got 20 boxes of eggs, which is 20 lots of 6, because there's 6 in each box. 2 times 6 is 12. Stick a 0 on because it's 20 times 6, not 12 times 6. So I've got 12 to 120. Now all I need is simplify. So let's simplify this down. First off, well, there is an easy one I can spot. And I'm not sure whether, well, it depends what you're going to spot. I think a really nice way to do it is thinking about halving it each time. So I could halve it and halve it and halve it until I can't halve it. And then think, well, can I divide by 3? Can I divide by 7? However, I can spot here, both these in the 12 times table. They're quite easy multiples of 12 to spot. That's 1 times 12 and that's 10 times 12. So if I divide both sides by 12, that's going to get the same answer as if I'd halved it and then divided by 3. So it's kind of this, it's the same thing, but I'm going to get there in one step. 12 divided by 12 is 1, 120 divided by 12 is 10. And the only thing I can divide 1 and 10 by, the only common factor of 1 and 10, is 1. So if I divide them both by 1, it's not going to change it. It's still going to be 1 to 10. So that is my final answer in its simplest form. So I'll just move this over. Ooh, I move my G's as well. Eggs. And because I'm really picky, I would like all these to be lined up there, like that. Right, so that is going to be 1 to 10. Lovely. Question 11. So we've got a diagrammatic sequence here. So that's a pattern that's made with a bunch of diagrams. And it's made to illustrate some kind of mathematical rule. We've got a sequence that has circular tiles, these grey circles, and square tiles, so a blank square. The first three patterns are this, this, and this. How many square tiles are needed to make pattern number 6? So let's have a look at the squares. So this is the squares. I'm going to do kind of a mini table here, not something very sophisticated, but I'm just going to have a look at, well, which pattern is it? I'm going to call that the term. So which pattern am I looking at? Term is just a word used in math to mean which item in the list. So that is term 1, 2, 3, 4, 5, 6. It will carry on, but I'm only going to go up to 6 because that's what the question wants. And then I'm going to do the number of squares. So how many squares are there? So let's have a look. At the first term in this sequence, pattern number 1, there is only 1 square. So that is just there, that's 1 square. In the second one, there's 1, 2, 3, 4 squares. In this one, there are 9 squares. Now, can you see a pattern here? Can you see what these numbers are? They're actually these square numbers. So 1 is 1 times 1, 4 is 2 times 2, 9 is 3 times 3. So we're getting the square numbers here, and the reason it's called the square numbers, the whole point of it, is that we're getting these shapes which are increasing squares. So they're not rectangles, they're squares. So that's why it gets its name. So if we carry this on, for 4, the fourth one is going to have, if you imagine it, a square with 4 along and 4 down. So that is 4 squared, or 16. And we could keep this going, 25. 6 times 6 is 36. So just doing the square numbers up, and that will get us how many square tiles are needed. So we will need 36 square tiles to get the 6th pattern. The next one, how many circular tiles? So again, I'm going to do another table, but this time instead of squares, it's going to be circles. This table just helps me spot that pattern. So that's circles. 1, 2, 3, 4, 5. I'll do it up to there. And you can see that for this question, we want the 20th one. Now, doing all the ones up to 20 will work, but it's going to be time consuming. And time is a precious commodity in an exam, so we don't want to waste it. So there will be an easier way to do it, looking at the pattern that's emerging. So let's have a look then. So for the first term, the first pattern, we have 1, 2, 3, 4 circles. For the second, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's all we've got. Now we need to look for a pattern here. So what's actually happening each time with these circles? First we had 4, then we had 8, then we had 12. We're actually adding 4 each time. So the next one, if you imagine it, it's going to have 4 along top, 4 along the side, 4 along the bottom, 4 along the other side. All together, it's going to be 4 times 4, which will be 16. In other words, I take the previous term and I add 4 to it. So if I was keeping it going, I'm adding 4 every time. That gets me to 20. And I could count up in 4s all the way up to the 20th term. However, there is another link here. Can you see a link between the term and the number of circles? What's happening every single time here? It's not adding, it's timesing. I'm doing 1 times 4, 2 times 4, 3 times 4, 4 times 4, 5 times 4. Every single time I'm taking the term and I'm multiplying it by 4. So that's what I need to do with my 20. So if I take 20, I do the same thing, I multiply by 4, and I get 80. So there should be 80 circles in the 20th term. Now we can imagine that since the first term just had 1 along the top, the second had 2, third had 3, the 20 is going to have 20 along the top, 20 going down, 20 going down the other side, and 20 along the bottom. In other words, 4 times 20, 4 lots of 20, which will get me my 80. Part C, Derek says when the pattern number is odd, an odd number of square tiles is needed to make the pattern. Is Derek right? You must give reasons for your answer. So let's investigate this. So when the pattern number, so we've called that the term here, when it is odd, so let's have a look at all the odd ones. So that is 1, 3, 5, 7, 9. Let's just do it to that for now. If we need any more, we'll investigate, but we'll see if we can spot anything from that. An odd number of square tiles is needed to make the pattern. So we remember the link for the squares. To find the squares, we took our previous number and times it by itself. We squared it. So the number of squares. So 1 times 1 is 1, 3 times 3 is 9, 5 times 5 is 25, 7 times 7 is 49, 9 times 9 is 81. So for all of these, this is true. What Derek says is true. When the pattern is an odd number, the squares of those numbers will be odd as well. Now, what reason is that? Why is that happening? Well, what we're doing here is we're doing the number times by itself. We're doing an odd number multiplied by an odd number. And an odd number times by an odd number is always odd. Odd number times by an odd number is always odd. That's a rule we can talk about. So if we're getting an even number, we're going to be timesing by an even, but an odd times an odd will always get you an odd. There is a proof for it that you do not need to know, but I am in the mood for tangents. I'm at 18 minutes, so as far as I'm concerned, it's a prime time to have a tangent. So just to prove it, you do not have to know this for your GCSE, so give it a skip if you're not interested. We have to come up with a letter. We're going to say K. We're going to put let K be an integer. So an integer is a whole number. We're saying K is any old whole number. Well, if I want to make this an even number, definitely going to be even, well, it's going to be in the 2 times table. So if I times it by 2, 2 times K, this is always going to be even because it's definitely in the 2 times table. And then if I get 2 times K and I add 1 to it, 2 times K add 1, that's always going to be odd because I've got an even number and I've added 1 to it. Now, we've got here an odd number, 2K plus 1, and we're going to times it by another odd number. Well, it's actually the exact same odd number in this one. We're squaring it. So we're going to be timesing it by the exact same odd number, like that. If we expand these brackets, so we get 2K times 2K, that's going to be 4K squared. That was this one and this one. This one and this one is, 1 times 1 is 1. 2K times 1 is 2K. 1 times 2K is 4K. There we go. And then if we factorize the first 2 terms, we can say that this is 2 lots of 2K squared plus 2K plus 1. In other words, we have 2 lots of a number, so 2 times something, then we've added 1 to it. So 2 times something, add 1. Well, we said earlier, 2 times something, add 1 is always an odd number. So this one, no matter what K is always going to be odd as well. So that's the proof that an odd number times an odd number is always an odd number. This is actually proved an odd number times itself, so squared, is always odd, which is also part of the proof. Now you do not need that for this. That was a big tangent. We just need to state this rule that an odd number multiplied by an odd number is always an odd number. Right, so let's move on. We've got 2 more questions to do in this video. There are only 7 blue pens, 4 green pens and 6 red pens in a box. 1 is taken at random from the box. What's the probability that the pen is blue? So for this one, we're going to be using a probability formula, which is the number of ways an event can occur divided by the total number of outcomes. Now, I word that differently every time I put it, but the basic idea is the denominator is your total, it's how many different options you've got with equal probability, and the numerator is how many gets the one you want. So this only works for fair outcomes, so biased events won't work. This is just for fair events. So a number of ways an event can occur. Well, the event this time is that the pen is blue. So how many different ways could we pull out a blue pen from this box? Well, there's 7 blue pens, that's 7 different ways. How many total number of outcomes, so basically how many pens can I pull out? Well, there's 7, then 4, then 6. If you add all of them together, you will get 17. So it's 7 out of a total of 17 pens. These are usually pretty well answered, the probability ones. Question 13, the diagram shows a tree and a man. The man is your average height. The tree and the man are drawn to the same scale. So that means that relating to how tall this man is, the tree is actually, in real life, that many lots of the man counting up. Write down an estimate for the real height in meters of the man. I think it's a weird question. It's a bit of a, I don't know, maybe a weird, tricky question, because usually in the UK we measure height of people in feet and inches rather than meters. So I'm not personally very used to measuring people in meters, but I got a rough idea. So average men from the UK are between 1.5 and 2 meters. So that's like a really big range, because 1.5 meters is about 5, no, I'm getting lost here, about 4'11". Should I know how to write it? Is that right? I don't know, that seems about right. 2 meters is about 6'7"-ish. It's pretty tall, pretty huge, in fact. So this is like a range, pretty much all men are going to be somewhere in between that. You get outliers, right? You get some exceptionally tall people, some exceptionally small people, but pretty much all people are going to be around that. And the average is kind of dead in the middle, about 1.575 meters. But I'll just go for 1.75 is what I meant. Like that. So I'll go for about 1.7, just as a guess. So that's somewhere in the middle of these. It'll be about, what's in the middle of them? 5'6", 5'7", 5'8", something like that. But it's kind of hard to work in the 2 different ones, as you can see, confusing my head. But 1.7 is about an average for a man. So if that is 1.7 meters, the next question says, estimate what the height of the tree is in meters. Well, we've already taken a guess at how tall this man is. So I'm going to see how many of these I'm going to need to fit the height of the whole tree. So in an exam, I'll be using a ruler and I'll be seeing how many of these little bits could fit into the bigger bit. How many is that then? That seems to go a bit above, doesn't it? But it's not been the most accurate of things. It's not an exact science, this. So I'd maybe go for maybe one below. So like maybe around here. Just kind of in the middle of them, isn't it? Let's go in the middle. So I've got 1.7 5 times, that's 5 lots of 1.7. So 5 lots of 1.7 is going to be 7.5? 0.75? What am I doing there? That's completely wrong. 5 times 1.7. 10 times 1.7 is 17. Half of 17. 8.5. 0.85. That makes more sense. So that's 0.85. It's not, it's 8.5. Okay, 8.5. So the way I'd work that out if I was doing a written method, I would do 5 times 17. 5 times 7 is 35. 5 times 1 is 5 plus your 3, that gets an 8. So 85, but it was actually 1.7, so I need 8.5 as my answer. And then we're going to guess that we've got probably about another half of that on top. So half of my 1.7, I just worked that out. Half of 1.7 is 0.85. So we get 0.85. I'm going to add that on to 8.5. Put this underneath. 8.5 add 0.85. That's going to be 9.35-ish. But there will definitely be leeway in this question. So if I just flick to the mark scheme, where's this question? Here. So this question is question 13, just on the bottom of that there. So we can see that the original was in the range of 1.5 to 2, so anywhere in between those two heights, 1.5 meters to 2 meters, which gives you quite a large range really. And then for the second one, we want either an answer in the range of 7.5 to 12, or whatever we put for the first bit times by somewhere in between 5 and 6. So if we look at what we did, we times it by somewhere in between 5 and 6, didn't we? Because I times it by actually 5.5, because I went 5.5 times up. So I took my answer 1.7 and times it by 5.5. I've probably done it a little bit too accurate there, to be honest. There was a bit too much working out for the marks available here, but it's a fairly accurate result. But we could have actually had anything in between all the numbers. It was quite a large range from what I remember seeing. This one. 7.5 to 12, so anywhere between 7.5 and 12, that's quite sizable, isn't it? We're on 9.35. Okay then, I'm going to leave it there for this video. So we've done the first 13 questions. We'll get into towards the middle of the paper. We've still got a few questions to go before then. If you're enjoying this series, do let me know. Do let me know if you want anything in particular covered. If this is useful, if it's not so useful, just let me know. I'm free to adapt. I'm going on a short break soon, but I'll try and film some more videos before then. But obviously it is coming up to exam season, so I want to provide as much as possible for you. So if you do want anything particular, now is the time to ask. Thank you for watching, appreciate it, and see you around.